Hi, my name is Matthew Mullis, and this is my Physics 2212 Lab Report 5. So, the purpose of this lab was to demonstrate the effect of Faraday's law in real life as well as in a computational experiment and compare the result of these. And so, in the experiment that we performed in real life, the time it took was 1.044 seconds, which I'll explain more in a minute. And on GlowScript, we found it to be 0.409 seconds. So some of the key concepts here is Faraday's law, which is this formula down here, the Biot-Savart law, which is a formula right here, Lenz's law, which is responsible for the negative in the Faraday's law, Ohm's law, which states that V equals IR. So our experiment consisted of dropping a bar magnet down a cardboard tube that was like covered in a bunch of loops of aluminum foil, and then recording the amount of time it took for the magnet to fall down the tube as the foil acted as a solenoid and greatly slowed down the magnet as it fell due to the laws that we stated previously. And so the tube had a length of 0.22 meters. I will explain further a little bit the other dimensions of it in just a second. But our different times we had for our drops was 1.13 seconds, 0.95 seconds, 1.08 second, 0.97 seconds, 1.09 seconds, giving us an average time of 1.044 seconds. And so the system was the tube and the magnet, and the surroundings were everything else. So here's the code that I used. And so the length of the tube was again 0.22 meters. The width of the foil was 0.006 meters, and the inner radius of the tube was 0.022 meters. So then set the mass and the magnetic field, or the mu of the magnet, and then the dipole B of the magnet based on mu and R, and then calculating the d flux dt. These are all different codes that I adjusted as needed to properly fit what I need them to do. And then again, using these values to help calculate, basically, as we'll see in these results, the velocity of the magnet and the amount of time that the magnet is within the tube. And so this is what the magnet looks like once it reaches the bottom of the tube. So the intensity of the coloring of on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise as viewed from above, and which counterclockwise, and how do I know this? So Lenz's law told us that the red is counterclockwise and blue is clockwise. What happens to the dynamics of systems when we flip the magnet around? The magnet will have the same descent as before because of just the different forces that are being acted, primarily the induced field and just how those work. Second half of this discussion, how does the total time and tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? And these were pretty different, and having more rings to properly model the solenoid could help make them more accurate, as well as just like more consistent recordings of time because it wasn't the most exact. And then how does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? And so gravitational force is greater than magnetic force at the ends of the tube, which is why we have these areas of non-constant velocity. But once it's inside the tube, they're equal, and that's why we have a constant velocity. What if? What if the resistivity of the conductor were reduced as close as possible to zero? How the dynamics of falling magnets change? As a result of Ohm's law, the induced current would become very big. The magnet would take much longer to go down the tube. And what if holes or slots were cut in the tube? How would this affect the ring currents in your model? The holes would reduce the number of rings in the tube, reducing the magnetic force in the tube, which would cause the magnet to fall down it faster. Thank you very much for watching, and have a great day.